Okay, so just to let you know, again, we're gonna do these three. Excuse me, the first two only. The third one is done in exactly the same way as step number 2. You can refer to your textbook, section 3, if you want some help doing that. So the first example we're going to work on is what's called a strong acid, strong base titration. In one of these titrations, what you have. Here, let me write the question out and I'll explain it to you. We're going to calculate the pH of a solution that contains 50 milliliters of 0.100 molar hydrochloric acid after the following amounts of 0.100 molar sodium hydroxide are added. Okay, now a little bit of setup. So we'll do a picture. This is different than what we've done previously. In a titration, you always start with a particular chemical. In this case, that's our 50 mils of the 0.1 molar HCl. We're going to slowly add amounts of a titrant, or something we're going to, it's opposite, a base in this case. At each step, we're going to add certain volumes. So for example, our first calculation will be after adding 0 milliliters of sodium hydroxide in this case. Okay? So we're going to calculate the pH at that point, and then we're going to add some base, recalculate. Add some more base, recalculate. Add some more base, recalculate. Now the difference with stoichiometry, the difference between these titrations and the calculations we've done in the previous videos involving, no strong acid or base, was that there is going to be a stoichiometry step here. When there are strong acids or bases present, we must consider their job first, their stoichiometry first. Okay? That's probably the major difference. Another factor that's going to come up is this issue of volumes. The volumes are in milliliters, and as you can see, we're going to have a whole sequence here. We'll do about 4, where we're going to add another volume. We're going to add another, like 10 mils, or actually we're going to add 49 mils. We'll get to that in a second, of the sodium hydroxide. Well, those volumes are additive. So in other words, after I add some sodium hydroxide solution to this mixture, the final volume is no longer 50. It has increased. So when we find molarities, you have to consider that total volume. Okay? Now, before we proceed with this calculation, it is going to go very rapid. I'm going to show you how it works, and then we're going to just crank them out, one after another. Okay? It's the same pattern every time. In any acid-base titration, there are 4 regions that you will have to do calculations. So let me write that down for posterity. And to be honest with you, these 4 regions are most important with weak acids or bases. The strong acid, strong base titration is very simple. You'll see that in just a moment. It's the weak ones which are more complicated. Here are the 4 sections. It always begins with an initial pH. That's part A that we're going to do first. You haven't added anything yet. It's just the original solution. After that, you have between initial pH and equivalence point. The equivalence point is that point where the amount of original substance, in our example acid, and the amount of the thing that's being added, in this case the sodium hydroxide, when those amounts are stoichiometrically equivalent, meaning they are both consumed. They are both the limiting reactant. That's what equivalence point is. Number 3 is the equivalence point itself. And number 4, after equivalence point. Each of those 4 regions has its own approach, but if you follow the sequence that I showed you in that first video of reading and identifying acids, stoichiometry first, then equilibrium, it's always the same. You're going to see that right now. We're ready to proceed? Okay, here we go. We're going to do the first step, which is after the addition of 0 milliliters of 0.1 molar sodium hydroxide. Okay, now, this is that category of initial pH. Same approach every time. We read the question. What chemicals are present that may affect the pH? Okay, well, there is hydrochloric acid, which we'll just write as H+, because the chloride is a spectator. HCl is a strong acid. I'll write HCl here in parentheses just to remind us of that. We also have we're not adding the hydroxide yet. I'm already getting ahead of myself. But we also have water. Which of those two chemicals is the greatest contributor to pH, or the strongest acid? HCl. Now you may say, well, wait a minute, you told me if there's a strong acid or strong base present, I need to do stoichiometry. Well, okay, you're right. So let's do our stoichiometry first to demonstrate how it works. Okay? So we do the stoichiometry by applying the strong acid to the, let me rephrase that. The strong substance, in this case the acid, does its job to completion, 100%. Okay? So in this case, here is the reaction that would happen. Do you understand? Okay, now, because there is no base present, it's actually not necessary for us to do stoichiometry. Excuse me, there should be a plus sign there. It's not necessary for us to do the stoichiometry in this case. You need to understand that when there is only a strong acid or only a strong base in the presence of water, it is a direct change on the concentration of hydrogen of water. In other words, there is no point in doing any equilibrium stuff. We could, if we want, please don't write this if you're in class, just kind of follow the reasoning. We could use the techniques that we're going to learn over and over and over and over, which is the following. For stoichiometry steps, we do initial and final, not ice. This is not equilibrium. We do the initial amount and the final amount. Now, if you remember in a previous video, I introduced the concept of millimole. So to remind you, millimole per milliliter is equal to molarity, or millimole is equal to molarity times milliliters. When we do stoichiometry, we need millimoles. So, if you look at the original problem, I have 50 mils of 0.1 molar HCl. 50 times 0.1 is 5. So I'm adding 5 millimoles of this to water, whose amount doesn't matter. I mean, we can call it infinity. There's a ton of it present. And so what's the limiting reactant here? Obviously this. There's 0 left. There's still a ton of this. There was 0 of this initially. We've made 5 millimoles of this. Now take a second to look that over. It's just basic stoichiometry. Do you see it? Okay. Now at this point, this is not molarity. This is millimoles. How do I find the molarity of hydronium after this stoichiometry is done? I divide by milliliters, which was 50, because I didn't add anything. You understand? 5 divided by 50 is 0.1. So in other words, the concentration of hydronium ions after this process is 0.1. What was the initial concentration of HCl? In other words, there was no point. Do you understand? We could continue with the pointlessness of this part by substituting into the law of mass action for water, if you prefer. We could do that. And remember, initial change, equilibrium, this doesn't matter. Oh, this starts at 0, this starts at 0. It's going to shift to the right, and this is going to, this doesn't start at 0. It starts at 0.1. It shifts to the right, so we get x, x, and we add down 0.1 plus x, x. What are we going to do with this change? Ignore it, because the K value is to the negative 14th, and the concentration of hydrogen is 0.1. In other words, there was no point in doing all this. Do you understand? So at the initial pH, there is no point in doing all these steps in the strong acid, strong base titration. All you had to do was realize that the concentration of strong acid was 0.1. The negative log of 0.1 is 1. So the pH here, 1. Do you understand? Okay. That's initial pH values. So let's go to the part B. This is that point between initial and the equivalence point. Okay, so at this point we're going to add 49 milliliters of sodium hydroxide. Excuse me, it's 0.1 molar, remember. Okay. Identify the chemicals that may affect the pH. I'll go ahead and write them as they exist. Are any of those strong acids or strong bases? Absolutely. Therefore, we have to do the stoichiometry first. So we have the following stoichiometry. The acid reacts with the base. I'll just show you the net ionic to save some time. To produce water. See it? Because it's stoichiometry, I'm going to do initial and final. The initial concentration of hydrogen. This is stoichiometry. This is not equilibrium. Therefore, we use moles, or specifically millimoles, because it's easier to handle. Okay? So to get the initial millimoles of hydrogen, I take its initial volume, 50 mils, times its initial molarity, 0.1. 50 times 0.1 is 5, a nice manageable number. If we had left those in liters, it'd be 0.1 times 0.05. We'd have a bunch of zeros in place. Not good. This is a much simpler technique. And then the concentration of hydroxide, since we added 49 mils of 0.1 molar, that's 4.9 millimoles. Do you understand? The water is irrelevant because it's a pure liquid. It won't have any effect on equilibrium for us. So, during this stoichiometry, what's the limiting reactant? Hydroxide, 0 left. How much hydrogen ion would be left, assuming a 1-to-1 ratio? 0.1. Agreed? Does everybody in class get that number? Remember, that's millimoles. And, in addition, it is a hydrogen ion. There is no point in doing equilibrium right now because it's a strong acid. It is not. We don't need to do ice for water. We just substitute the concentration of hydrogen directly in. We just find the negative log of it. Agreed? Do we take the negative log of this number? No! That's millimoles. So we have to divide by milliliters. What is the milliliters now? 99 is the correct answer. Because remember, we had 50 mils of the acid, and we added 49 mils of this. Agreed? So you have to take 0.1 divided by 99, which will give you the molarity, the concentration of hydrogen ions, and then from that you find the pH. It comes out to be 3. Please prove it to yourself. We'll do it. Take a second here. 0.1 divided by 99 equals negative, or excuse me, 0.001 with some digits. We'll take log of that number, 2.9956, which rounds to 3. Do you understand? You sure? No? To watch it in the video. I don't have time. I'm sorry. Okay. So, for part C, we're going to add 50 milliliters. Okay. Our original question, original problem, we had 50 mils of acid, of 0.1 molar acid. And we just added 50 mils of 0.1 molar sodium hydroxide, a base. What can you tell me about the moles of acid and base present now? Stoichiometrically equivalent. In other words, this is the equivalence point. Do you understand? But we can prove it. First, identify the chemicals present that will affect the pH. Are any of them strong acids and bases? Yes. So we have to do stoichiometry first. I'm going fast because it's the same pattern over and over and over. Excuse me, last time I used H+, so I'll do it again. H+ from the HCl plus OH- from the hydroxide makes water. Because it's stoichiometry, I'm going to do the initial and final amounts. I'm going to use millimoles. The initial millimoles of hydrogen, 5. 50 times 0.1. How many millimoles of hydroxide did I add? 5. 50 times 0.1. Agreed? Okay, so what's the limiting reactant? They both are. So at the end of this stoichiometry process, what chemicals are present that may affect the pH? That's it. And if that's the only chemical present at the equivalence point, do we need to set up an equilibrium to determine its concentration of hydrogen? No. What is the pH of pure water? 7. The pH at the equivalence point for every strong acid, strong base titration is 7. Why? Because they've both been consumed. They've been neutralized, leaving behind water. Get it? Okay, last. Slightly after, we'll go 51 mils. I'm showing you the 4 regions here. So I'll go quickly. I'll save some steps. Remember, HCl, sodium hydroxide are present. They are strong acid and strong base, so I do stoichiometry first. Same pattern. Initial, final. What is the initial concentration of hydrogen ion in this example? Or excuse me, the initial number of millimoles? 5. What is the millimoles of OH added? 5.1. 51 times 0.1. Do you understand? Okay, so what's going to be the limiting reactant? Hydrogen ions. There is 0 of it left. There is an excess of 0.1 millimoles of hydroxide left. Agreed? To find the pH of this solution, I got to take the dominant acid or base left. And in this case, there are 2 chemicals left over. Excess hydroxide and water. Which one do you think is the strongest or largest contributor? Hydroxide. It's a strong base. Do I need to do equilibrium for a strong acid or base? No. It directly affects the pH, the equilibrium of water. So I'm going to have to find the negative log of its concentration. Or in other words, I'll find its pOH and then convert to pH using the relationship pH plus pOH equals 14. Agreed? So the concentration of hydroxide is the excess amount divided by the total volume in mils, which is 101. And then I'll take the log of that number, the negative log of that number actually, to get pOH. So negative 1 divided by 101, let me do it on my calculator real quick. And then take the log of that number. I get a pOH of 3. My answer, of course, is 11. Do you agree? Now, this is an important thing. I want you to see this. If you go back through the problems we just did, you just noticed that the pH went from, the equivalence point was 50. So if we make a graph right here, here's pH over here, here's the milliliters. If we call this 50 mils, that was the equivalence point. The pH began down here at about 1. And when we added 49 mils, so we were about right here, the pH was 3. Was it 1 or 2? I forget what we started at. And when we added 49 mils, the pH was 3. When we added 1 more mil, what was the pH? 7. When we added 51, 1 more mil, what was the pH? 11. Look at that. An incredible jump in pH around that equivalence point. This is not a buffered solution. The pH change, especially right there, was skyrocketed. Do you understand? So it was roughly flat along here, but then it skyrocketed. Now, when we do the weak acid, weak base thing, one of the differences you'll see is that the equivalence point will be much smaller. The curve will look more like that, whereas we just saw one that this one that I'll redraw in red is indicative of a strong acid, strong base titration. A drastic pH change at the equivalence point. A weak acid, it shows a more gradual, like the blue line there. Any questions on that?